Let me start with a question. What is a computer? Today, we typically think of a general-purpose machine that can do just anything. I can read my emails, watch a movie, or calculate the location of the planets on the night sky, all with one machine. That's in stark contrast to the Antikythera mechanism of the old Greeks. This is also a computing machine, but tailored towards just one question. What is the relative location of sun and moon on the sky? So how does this translate to the quantum world? What is a general-purpose quantum computer? A general-purpose quantum computer takes instructions, operates them on its quantum hardware, and gives us answers. This can be cracking the RSA encryption. This can be sorting large sets of numbers, or just anything someone writes an algorithm for that can be executed on this machine. But we learned today that it might be hard to scale that machine up in the near future. So maybe we should do it like the old Greeks and build a single-purpose machine, a quantum computer that can answer just only one question. Now we need to find a question that is worthy of building a single-purpose machine. Many of today's technologies that will still our energy hunger for the future produce electricity far away from where we need it. That presents us with the problem of transporting electricity over long distances, which is typically full of losses, and we would like to avoid that. So this is a problem we try to address. Now, luckily, we have a class of materials that do exactly this. They're called superconductors and can conduct electricity without any loss. So everything is fine. We're done. Unfortunately not. After more than 100 years of research on the topic, we do not understand them well enough. We tried hard. We do understand certain classes, not the others. Since 25 years, we're almost there. We almost managed to cast them into a useful everyday technology. But we still fail. Almost seems not to be good enough. So now this is our purpose. This is our question we build a single-purpose machine for. This quantum machine will give us one answer. How do I cook up a material that can conduct large quantities of electricity without any loss from A to B? So that's what we're going to build. But now we have to ask ourselves, what are we actually trying to understand? What is the task of understanding a superconductor? Superconductors are made from really tiny, complicated quantum systems, billions and billions of them, and they all interact strongly with each other. So understanding this tiny quantum system is our task, and we seem to fail at it. So what we should do, we should take this tiny, complicated quantum system and map it to a much larger quantum system. A large quantum system that we don't understand either, but one we have under precise control. We let this large quantum system simulate the small quantum system we try to understand. So what is the simulator giving us? The simulator is telling us we think a certain model describes superconductivity. The simulator solves this model for us, and then we can take the next step in engineering new materials. At the heart of such a simulator, as well as at the heart of a multi-purpose quantum computer, is the precise control of quantum systems. This includes their almost perfect isolation from their environment, because quantum systems seem to be terribly susceptible to influences from the outside. So maybe we can turn this sensitivity into a technology for the future. QNAMI, a startup from the Swiss quantum ecosphere, is doing exactly this. They provide quantum engineered diamonds for quantum communication or nano-MRI purposes, and they transfer this technology to the semiconductor industry for the diagnostics of integrated circuits. Luckily, only thinking about quantum systems helps you to engineer totally classical things. In my own group, we devise new mechanical metamaterials that we wouldn't be able to do without our training in thinking quantum. Understanding how quantum systems dance together is at the heart of building a quantum computer. But I hope I convinced you that along the way of trying to solve the problem of getting a quantum computer, we'll have many side paths that will allow us to have equally disruptive technologies. Thank you.